one more episode of the Type Theory for All podcast. As always, this is your host, Pedro. And in this episode, we continue the conversation we were having with one of the Rocq core developers, Pierre-Marie Pédrot. It's a continuation of the previous episode, but if you didn't watch, don't worry. They are not necessarily related in any much sense. So in this episode, we are going to get even more theoretical into Pierre-Marie's interest. Since his PhD, he's extremely passionate about Gödel's incompleteness theorem and a particular instance of the Curry-Howard isomorphism that he was working on called Dialectica. And that's all related, revolving around this notion of realizability and even continuation passing style. I'm not going to try to give much detail on what those things even mean because I think he did an incredible job explaining those in a quite accessible manner. I'm very, very confident you guys will love this episode. But before we get into that, quick message for you. Here at Type Theory for All, we have a mission with open access and open education. We abhor the possibility of getting our content locked behind some kind of paywall. So in order to help us to deliver to you the best of type theory, programming languages, and formal methods for free, we humbly request your support through Ko-Fi. Simply go to our website, typetheoryforall.com, and follow the prompts. A donation of any amount, even $5, will be of a great assistance to our cause. Also, don't forget to follow us on Twitter at TT4All and joining our Discord. We're currently organizing a weekly study group to learn Rocq through software foundations. So if you think that's something you'd be interested in, go to the website and join Discord today. Okay, so realizability.
Yes. So there is a joke saying that the first rule of the Realizability Club is to be able to say realizability. I know that the joke has been said. I can go on serious topics. So realizability is a family of techniques that are used to somehow give models of logic. So I'm going to take a very historical stance here. That's how it was conceived at the time it was first introduced. So there are basically three historical realizabilities. There is for a reason that will become clear soon, you will see why. There is a Kleene realizability, Kreisel realizability, and Gödel's realizability called Dialectica. Okay, out of which I can generalize the statement saying that all realizability need to have a name that starts with K, which also works for classical realizability because it's actually Krivine's realizability also starts with a K. So if you have a name that starts with a K, you have to cook up your own realizability. Right. So I think that the original motivation for realizability was like precisely one of things I touched a little bit before, which was like the crisis of the foundations after Gödel incompleteness theorem. So they were still trying to get a finitistic, whatever that means, interpretation of logic. And the fact that there is a program that realizes a formula, like there is a concrete object that is somehow a proof, is a finitistic approach. So realizability is about interpreting a logic into a programming language with a few side conditions on the programs that. So you typically, like in the case of Kreisel and Kleene realizability, they are very similar. Morally, in one case, you target some kind of a variant type language that has like Turing machines. You could do it with a lambda calculus, but you have to be a bit careful. That's Kleene realizability. And Kreisel realizability is targeting basically simply type lambda calculus, right? And in both cases, you make the BHK interpretation as the heart of your interpretation, right? Of your meaning explanation for your logic. So you say that, for instance, what is a proof of A implies B? It's something that given a proof of A, so it's a process or a function that given a proof of A produces a proof of B, right? So okay, so you already see that where I'm going because you're writing a program that is like implementing an implication in the like a narrow time, right? Same thing for like all the rest, like all the connectives such as or what is a proof of A or B? It's either a proof of A or a proof of B, blah blah blah, and this is how you go. Realizability is precisely that where you interpret hidden computational content in your logic, but you make it explicit by writing realizers, so somehow hidden proof terms, so a simplification, an erasure of the proof term as a program, right? So Kreisel realizability can be, I mean, we would call it probably extraction nowadays. Kleene and Krause are very similar, so Kleene as well, I guess. So it's nowadays like there are in from the point of view of the Coq system, there are basically erasure, like extraction. You take your logic, you interpret it computationally, and then you erase the parts of the logic that you didn't care about. And it was so it's a general technique that can be used to prove that some principles are consistent with or inconsistent with some logic. So typically, with linearity, you can prove that what Markov principle is compatible with a Heiting arithmetic. With Kreisel realizability, you can prove that what independence of premises and stuff like that, I guess. So it's a way to give a specific kind of model to your logic. And there are a lot of realizabilities, like a lot of people have come up with a different system. So for some weird reason, people are very insisting on the fact that you only care about some specific kind of side effects. So in the case of Kreisel realizability, there is morally no side effects, although this is not completely true. And in the case of Kleene, there is one side effect, which is non-termination. You can have like Turing complete target. And you have the other more fancier realizability, so Dialectica, but maybe we're gonna come back to that after that. That one is doing something different. And you can also see classical realizability as a specific kind of realizability, where instead of targeting the simply type lambda calculus, you are basically targeting lambda calculus plus cold CC. So you have more computational power. More generally, it could be said that empirically, it's not a formal statement once again, but all reasonable realizabilities I know of can be factorized as like Kreisel realizability, like the no, I guess the vanilla realizability. You just say that's a way to give a meaning to BHK somehow, like that the most neutral thing, plus a logical interpretation, and that makes some kind of diagram commute. You can also phrase it as a program translation. So it's either a logical interpretation then interpreted as HA, or through Kreisel, okay, or an interpretation into a system that has additional power in the computational world that you eliminate away with a program translation. So Krivine realizability is like that, for instance. Typically, you can present Krivine realizability as a composition of Kreisel plus double negation elimination, or if you go the other way around in the diagram, you can write it as exactly. You can get rid of so you get Krivine realizability and you can get rid of cold CC by doing a CPS translation in the programming world and as well in the realizability.
What is BHK interpretation?
The
BHK interpretation?
BHK, so Brewer, Heiting, Kolmogorov. So it's basically the meaning explanation, as in per Martin, like the type theory paper, of the intuitionistic fragment of logic. So it says, what are the normal forms of your programs realizing a formula? So A or B is A or B. A implies B is something that turns A into B. So it's just paraphrasing what the realizability interpretation does. Okay. And it's not the case in classical logic. There is not. It's not true that for instance, the interpretation of OR in classical logic does not obey this property. Because as I said before, there are Booleans, which are some kind of OR, like they are glorified OR if you want. There are Booleans that are neither true nor false in classical systems. And they wouldn't satisfy this. A proof of A or B is either a proof of A or a proof of B. You have to give one side. So
the BHK interpretation is what we more often call nowadays intuition, not necessarily just intuitionistic logic, but something that
it's a principle. So it's not a formal thing. It's just a guiding principle for the intuitive meaning of the objects you are manipulating.
Right.
And it can be made formal through realizability interpretation.
Exactly. That exists the program that makes this, like that gives me the actual content of the proof. Right. But this was, for historical reasons, was when they were still discussing these ideas in a philosophical...
Yeah, so there's a lot of weird things going on there, yes.
So nowadays, what we call realizability and really realizers. And
I mean, it's the underlying philosophy behind the realizability approach.
Mm-hmm.
Okay. So now I can start ranting because I love ranting. So to me, realizability, I can be considered to be studying realizability in my daily research, I guess. But I have a kind of qualm with most of the people doing realizability nowadays, which are somehow stuck in the 30s or 50s at best. Because there is something much better. So, okay, So what is realizability about? Okay, let me rephrase and let's be clear that there is a trivial solution to this problem that is much more elegant. So realizability is like, oh, my proofs have a computational content, right? And I'm going to represent them as programs. Well, let me think for a second, okay? But why do I have to go through this kind of weird interpretation? Why am I not just adding the proof directly in the system, right? No. And then I would be able to reason directly about the proof without this fancy realizability layer that is hiding a lot of things. And then I could actually, instead of pretending that I can extract my programs, I can actually manipulate them as a first-class thing, right? And then there would be exactly what I'm looking for. Okay, what I've just described is literally Martinov type theory, right? So when you do Martinov type theory, the question of realizability is moot. So like you have designed your system, like it's not even that you have to do, like there's nothing to do because your system is by definition already a realizability interpretation. Yeah. You have a way to evaluate, like you take your program, you run it. There is no, like a proof is a program, right? There is nothing to extract because it's there, right? So you can always argue that, oh yeah, but there's erasure or something like that, but it's kind of true. But this is kind of missing the point that if you can go directly for a system that is baking in the design principles of the BHK and in realizability approaches, then why don't you do that, right? There is no need in today's world. Most of the things you can do with realizability have been made intrinsic to Martinov type theory. A good chunk of what people are insisting on in the that's what I call the dusty logic, like the people from the I'm going to bitch about the Germans, but okay, it's a German thing for some reason. Like Germany has a long-standing. I've got very good German phrase. You can ask Yannick, for instance. I think he kind of agree with me. We had a discussion recently about the use of parenthesis, a use of the type systems where you use his PhD advisor insisted on using a specific letter, the very same specific letter for all instances of programs with the same type, right? So, okay, instead of giving program names, you have to use the same Greek letters because they have the same type. And the way they're all the fucking same letters, and the way you discriminate them is by adding indices when you need to make them to actually realize that not the same. So it seems to be a German thing to be stuck somehow in the I'm not going to make a Godwin statement soon, but we're not very far from it. So there is a thing like Sweden has come up with a perfect specimen or called Per-Martinov, who's designed this marvelous system of Martinov type theory. Please use it. Stop trying to go through weird circumvolution of parameter of realizability. And the funny thing is, so you can port all the parameter, the realizability approaches can be ported to MLTT. Like, it makes sense. But you don't have to have this weird system where you say, oh, on the one hand, I have a programming language. On the other hand, I have a logic to reason about my programming language. Because these are the same. You don't have to separate anything. So all these interpretations can be still performed as program translations. So that's the heart of my research program. Like, you want to write the program translations that you would write. So remember the diagram I was talking about before, like the thing that makes the realizability commute with a program interpretation in the target. You could even squeeze that square further, saying, yeah, there is no need to make a difference. These are the same things if you use the rich enough target theory, which is like Martinov type theory or any kind of fancy type theory that requires more things. But basically, if you accept this proof as program identification from the start, then suddenly a lot of things become much more elegant and much simpler, because there is no need to do artificial separations between things that are the same. So for instance, like this weird artificial separation between the arrow and the pi type. Okay, so in Martinov type theory, the arrow is a special case of the pi type. And if you look into the realizability interpretation, that's the case for all realizability interpretation. So recently, Valentin Tableau gave a talk where he insisted on the interpretation of for all and arrow of the dialectic interpretation. And if you interpret for all as if you interpret for all as a dependent arrow on natural numbers, then the two collapse because they are the same. So it's very weird that there are still people arguing that these things should be separated when all models they are considering. So I'm putting aside, the weird people doing reverse math or stuff like that. But in the PLT/realizability world, it's very weird that there are still people insisting very adamantly that you should separate arrow and for all when they are interpreted the same in the model, because there are it's like a given of Martinov type theory that these two things are actually basically the same thing. One is a degenerate version of the other. So it's a bit weird. So realizability, where were we at?
Okay, so as a summary, so we have Kleene, Kreisel, Gödel, and Krivine realizability.
Yep.
Let's see if I got this right. So Kleene realizability, it's something related to Turing machines. What
you target your language of realizer. So the two important things is that you have non-termination, so your target is Turing complete.
Right.
And furthermore, you have access to the actual code of the machine. So if you had to replicate that as a lambda calculus, you would need to have like a lambda calculus with fixed points plus a quote operator. Like you need to be able to say, oh, here is the code of my machine, of my program.
And then Kreisel is the lambda calculus.
Simply typed, yeah.
And then Krivine is lambda calculus plus call CC.
Yes.
So you can talk about the classical logic.
Yep.
What about Gödel?
Aha, so we are now going to Dialectica world. So Dialectica is a funny thing. So let me tell you an anecdote, which is about my PhD. I love talking about my life. So
that's not true. We talk very little about your life.
Okay. Let me allow to talk about my life. And when I was younger, so it was quite a bit of time ago already. It was at Types 2013. So precise. So Types 2013 was in Toulouse, in France, and I was a bit desperate because it was like I was in my second year of PhD somehow, and I didn't know exactly where I was heading to. So I was kind of a bit desperate about what was going to happen to me, because the original topic of the PhD was not really very fruitful.
And you were already studying with Hugo.
Yeah, I was already. There was this very depressive moment where I mean, I thought I would defend my PhD and whatnot, but I was a bit wary about what would my PhD become. Either something very short about like some trivial stuff you have to write, and you don't do anything very interesting, and you're not extremely proud of your PhD, but you got the PhD because of whatever, And there was this magical moment at Types where we went to a restaurant. I think it was the social event or something. So I was at the table with, on the one hand, Colin Ribat, who I knew from the ENS of Lyon, who was a teacher at the ENS of Lyon. He was freshly recruited, maybe. It was when I arrived at Lyon, I think it was his first year or something. So a few years before, I was at the ENS Lyon. So I knew him from there. Colin Ribat, a nice guy doing precisely this kind of German stuff. He came from the rewriting community, I think, originally. But he taught, at least maybe he didn't study it, but he taught us these realizability kind of stuff in one of the most violent classes I've ever had in my life, which is basically trivializing the master I had in Paris. like I was at the master one at the ENS,
right.
And Colin, seemingly from what I learned, I'm opening parentheses about my life, I'm sorry, but from what I learned, he was kind of frightened about the fact that, the Normalien students were the elite class that we were talking before.
Yes.
That these people that were asking a lot of, they were you had to feed them with very serious stuff. So he gave everything he had. And in 1 year, a single 6-month class of Master 1, I got literally more than what I got in a Master 2, the whole Master 2 I did in Paris the year after that. So most of the things I saw in Paris, I already saw that in Colin's class, not very interesting, blah, blah, blah. So that was really... So I guess I'm very grateful for this class, by the way. And Colin was there at the table, so it was my entry point in the conversation. And next to him was Ulrich Kollenbach, was the Dialectica man, a very famous guy who's the leader of the proof mining research program, which is basically you take these crazy proofs in classical mathematics, so about analysis or something of some kind, right? You write this in some fancy subset of second order arithmetic. You put that into a horrible machine called Dialectica. It spits out horrible proof terms, but in the end, you get like interesting bound analysis through majorizability or whatever it's pronounced. So so he's like a heavy user of Dialectica. And the conversation actually started talking about Dialectica because we've got like the international expert in Dialectica here. And it was very weird because like Colin was trying to convince me. So I have a distinct recollection of this moment. So Ulrich was not saying much. He was like nodding most of the time. And Colin was like the real driver of the conversation. And he was saying, so, there is this dialectic interpretation. So it's very fine piece of Gödel's work, mysterious. There is no way it can have a Kerry Howard interpretation. So like it goes beyond Kerry Howard. It's something that cannot be turned into a proof as program interpretation. So that was basically the gist of the conversation, and it stuck in my head. And I was like, oh well, why not have a look at Dialectica, because like it's. Like Colin seemed to be like amazed by this thing. So I looked into it and I realized that there was it was perfectly explainable in terms of simple things that are not related to this horrible German style obfuscation and whatnot. But more than that, it actually is a program translation. So it has a very nice explanation in terms of Kerry Howard isomorphism. So I would like, to thank both Colin and Ulrich for like literally finding the subject of my PhD that night, more precisely. And the only reason I actually did it is like to prove them wrong. Like so listeners, please remember, like if some very important person from wherever, like if an expert tells you that something is not possible, or at least believes it's not possible, like you should really look into it before making your opinion. And then they may be right because they are experts after all, but sometimes they are wrong, and there are a lot of things to actually extract from the fact that they are wrong. Okay, so that was so I did my PhD on the computational study of Dialectica, and the funny thing is that it's something. So I understand why, from the point of view of Gödel or the German style logic, it's very hard to explain what it does computationally, because if you don't have the right language, once again, we come back to the problem of language. If you don't have the right language to phrase what it does, then it's very clunky to understand what it's actually doing. And forget about realizability. It's really just adding the same way that the classical realizability is adding cold CC. So in classical realizability, you can backtrack. Like cold CC tells you, I can store morally, I have a first-class notion of continuation that allows me to capture like some kind of snapshot and backtrack to that snapshot whenever I realized I made an error. Kleene gives you non-termination and quote, so that like you have arbitrary fixed points and stuff. And you can wonder what Dialectica gives you, because it's actually a very nice side effect. And morally, and I think I'll come back to that after, but let me give you the motto first. So basically, Dialectica gives you a way to track the uses of your variables in functions. So somehow, I'm saying somehow, if I give you a function in the dialectic interpretation, not only this is a bona fide function as you would get in BHK, so it's something that turns a proof of A into a proof of B, but it's also something that there is like additional data that is telling you how this function, proof of A to proof of B, how this function is using its argument. So it's gonna give you a generalized notion of the number of uses, like some kind of measure of the uses of the argument of the function. So it's a way to morally, if you want, it's somehow instrumenting what we call dereferencing in the Krivine machine. So, the moment where you've got like an environment, like pick your favorite machine, like the SCCD, the CAM, the whatever, there's always one operation that corresponds to looking up a variable in the environment. Like you have a closure, right? You look up a variable in the environment. That's the thing that there is in all the low-level machines. And morally, what Dialectica does is to say, the normal interpretation is just fetch the value of the variable and carry on. But in the case of Dialectica, you remember that you actually did something there. So you're storing on the side a little thing saying, you actually accessed that variable at this point. And with that, so in particular, that gives you a way to count. So you know how many times your variable are used, but it gives you a little bit more than that. In particular, it gives you a way to constructivize negation, because a negation is somehow going to tell you some information about how because if you have a proof of not A, then if you have a function that uses that, okay, either the function doesn't use it at all, then it's not very interesting. But if your proof of not A is used, the only real way to use the proof of not A morally is to give a proof of A, right? So like you want to derive a contradiction.
Right.
So morally, it's constructivizing this ability to actually like track the uses of the arguments is gonna give you a way to somehow extract a weak form of A when given a proof of not A morally, like your very weak form of that. So it's like extending Dialectica is weird-ish in that view. It's like it's clearly intuitionistic in some sense. So it's intuitionistic because it preserves the canonicity property we're talking about. Like the witness, it's also called witness property or Boolean disjunction, whatever. The fact that if you have a proof of A or B, then it's either a proof of A or a proof of B. If you have a proof of an existential, then there is actually a real value there. So this is preserved by Dialectica. But at the same time, you get inside some kind of very faintly classical content that allows to extract non-trivial information from proofs of double negation. And I think that's the crux of the Dialectica interpretation. And the thing that I think is worth mentioning is that remember that I said that it was giving you a way to measure the number of uses, right? And it's actually not surprising. Why? Because like there has been a wealth of work at the beginning of the 90s by De Paiva between others. So Valeria De Paiva worked on like a categorified variant of Dialectica because they realized that this realizability model sort of were a very good way to construct models of linear logic, right? And then this bridges the gap because like, okay, you have something that counts the number of uses. Okay, so how do you get the linear function? You say, oh, it's only using its argument once. And that's how you close the problem. So Dialectica and its generalization known as a double gluing, which is like an extremely a bit arcane construction due to Highland, I think, which is a generalization of the dialectic interpretation. There is some empirical observation that most of the models of linear logic are actually an instance of double gluing. So some kind of generalization of the Dialectica interpretation. And this is no wonder because like really that's the most natural way, like the Dialectica translation is really the most natural way to add a way to count how many times you're using your arguments. So this is a very funny side effect. It's not the usual kind of side effects because if you do like say for instance if you do side effects in I don't know, pick Haskell, for instance, and you do monadic encoding, you won't be able to see that because you will always interpret the arrow as in the monadic translation, you interpret A implies B as A implies M of B, where M is your monad. So somehow you are saying, yes, an arrow can have like a effects on the right-hand side. So when you call a function, the result is going to do weird things like not terminate or modify the state, blah, 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 raise exception, whatever you want. But here, Dialectica is doing something about the argument of the function. It doesn't tell you much about the actual result because the result is pure and it's still satisfying the nice disjunction property or witness property. So you still have canonicity. But functions now are weird. Like the functions are the things that are telling you something about their arguments, which is not something you can really explain in terms of monadic translation. So you can't really write that as a monadic translation in whatever the target. And also, once again, to complain a little bit about the dusty German logics, it's something that is a complete non-object if you're thinking in terms of derivation into whatever second order arithmetic. Like, what the hell? Because like, what the hell is dereferencing in second order arithmetic? Like, to explain properly what Dialectica does, you need abstract machines with a dereferencing operation. And there is no such thing if you just look at your derivation. What does it do? Something. So by framing carefully the realm in which you describe your object, suddenly like what it's doing is becoming utterly clear. And now it's even worse than that. Now I'm saying Dialectica all over the place. Like every time I look into a linear logic model, I say, That's a dialectic interpretation. Yes.
Okay, so that was a lot, and I'm having trouble. Like again, I don't want to make it.
Yeah, you should interrupt if you have like misunderstandings or like utter confusion, because these are things that take a lot of time to really
digest.
Yeah.
Yes. Okay, so again, we have different notions of realizability, with different effects that are put that way. So what the effects that the Gödel realizability is giving is an even stronger notion of linear logic, right? Because linear logic is like use your variable once. This one is like
you can have more than like a actually. So this is something I'm working on currently. You can subsume what is called gradual types with Dialectica models. So not only you can say that something uses its argument once. So the criterion is more subtle than that. So it's not only this whole mess about using variables once is an artifact from the syntax. Like people have been obsessed with that in the linear logic community. Like, it's very important that you use your variable syntactically once. But in practice, linearity is a more, how would I say? Like, it's not that it's more general, but like it so happens that in most of the cases, it's partially captured by this criterion of using the variable once. But I think it's a bit of a red herring. Mm-hmm. Like the real property you care about is talking about side effects. And Guillaume Munch-Maccanini from the Galilei team wrote quite a bit ago a very good generic definition of what it means to be linear, and it has no link whatsoever with like you can phrase what it means to be linear in an arbitrary call by name lambda calculus. And I think this is once again a marvelous definition because it coincides with all the historical. If you look into the historical definitions, the historical models of linear logic, this notion of linearity, which is an equational property of, it's a very easy thing to write. It's an equational property of a lambda term. So you can write it in simple type lambda calculus, so whatever, in anything that's called by name lambda calculus and whatever types you take. And it coincides if you compile it into the standard linear models, coherent spaces, totality spaces, where you name it, you will get the usual notion. So empirically, this really captures the notion.
And why does it have to be called by name?
Because otherwise the equation is trivial.
Okay.
Yeah. So.
Oh, okay. It's that thing that we were talking yesterday about the boxes.
Yes, exactly. Right. So linear logic is heavily biased towards call by name. I mean, marginally, people doing lambda calculus and type theorists in particular, if I may slightly go back to what we were talking about before, there is an extremely strong bias for call by name. And the reason is that as soon as you have a substitution that is unrestricted, like you can substitute a variable by an arbitrary term, then you're like by definition called by name. If you don't have a notion of value, somehow you are bound to be called by name because like you don't really see a thing. And this bias is pervasive in the study of lambda calculus, and it leaked into the linear logic community because if you look into linear logic, like it's heavily biased toward call by name. If you want to do a call by value interpretation, you can see just by looking at you may know about the two famous translations of intuitionistic logic into linear logic. So there are both due to Girard, but one is called Girard's translation for some reason, and the other one is called the boring translation. I didn't make the name. It's called that way. So the Girard's translation is called by name, and the boring translation is called by value. And if you really try to do the boring translation properly, you realize that it's not as easy. You actually need something on the side, like you need to check that something is a bang algebra or a quadalgebra or whatever. So there is an inherent bias towards call by name in linear logic.
That's funny. That's when I thought call by value was usually the de facto used for everything type theory, PLT related.
And PLT maybe because that's more efficient. But as soon as you turn to dependent type theory in particular, like everybody is called by name, because like just by virtue, if you can substitute a variable by an arbitrary term, you lost. There's no notion of value in MLTT, and this is quite an annoying bias because I like to liken it to hemiplegy. If you only do call by name, typically, so there is worse than only doing call by name. There is doing call by name without the positive connectives, because like here you're really missing half of the picture. So the only place where you have a bit of call by value and call by name, if I might say, is for the primitive connective, so the inductive types, because pattern matching needs to evaluate its argument before doing something. Yep. So it's the only place where you can force computation to happen in call by name, And if you don't have that, which is the case of many people studying lambda calculus, so if you only have like arrows and substitution, then you are basically lacking half of the picture. So your life is easier because you are ignoring the problems. And yeah, if I can make a little bit of advertisement, I think people should look really into call by push value, which is like a wonderful system that synthesizes that prevents the hemiplegy. Because like call by value has another kind of a blind spot. So okay, as call by name is blind to forcing arguments, call by value is blind to the fact that some things can be pure enough. Because like when you write an arrow in call by value, it's necessarily a impure arrow if you're living in a morally impure world. So when you write A to B to C in call by value, then if you look in for instance, a monadic translation, you would get A to T to B to D, C, right? So you get two nesting of T's. Like,
right.
So every time you have an arrow, like some effect might happen. And if you look into the implementation, this is not even true. Like on your camel, for instance, there's a little bit of like a fun anecdote. There's a little bit of runtime typecasting or whatever you call that, which is in the arity of functions, because functions in a camel have arities, right? And there is dedicated code to say when you apply a function to an argument or to several arguments, there is a little bit of code saying, is the number of arguments smaller, equal, or larger than the arity of my function? And that's morally a little bit, a very tiny bit of a runtime typecasting that is happening at this point. Because like if you had a finer type system, you could say this function has arity whatever, and doing the application is actually doing something fancy. So yeah, that's the blind spot of the call by value world. Like they have no way to say that something is staying purely in the world where the effects are pushed to the outer edges of the computation. They have to happen every time.
So call by push value gives the best of both worlds.
Yes, it synthesizes.
It allows some parts to be called by name, some parts to be called by value.
You can compile both call by value and call by name into call by push value. And like once you've seen call by push value, it's like Dialectica, you will see it pop up everywhere. So the same way you see Dialectica pop up everywhere in linear logic, call by push value, you will see it pop up everywhere in PLT. It's everywhere.
So Dialectica, it's kind of like, in many senses, also filling the final gap of maybe I'm getting a little too far, but from what I understand is once we're looking at the Curry-Howard isomorphism and proofs are programs, and then once you add call CC, now you're starting to look into this notion of side effects and like adding the Curry-Howard isomorphism into the realm of side effects and really noticing how even a logic or a programming language that is taken into consideration, classical logic, you still can realize that in some notion. And now with Dialectica is adding even more power to that, where you
well, so I don't think it's about power. It's all about trade-offs, right? And the same way that there are reasons why you wouldn't want your theory to be classical. Because it's all about trade-offs. Like if you add call CC, you weaken the shape of your normal forms. Because like suddenly you get these weird booleans that do not really exist.
Right.
So that's so it's not because you are more expressive in terms of computations that you are better. You can do more, true, but you can expect less. So
I think the point that I wanted to make is that you are getting more choices as a developer of a language of the things that you can achieve. You know what I mean? So like now I get this point of like, okay, in my language, I can realize this logic that is excluded middle. Now in my language, I have a good model on how to realize the logic where things are linear, right? And so on.
So it's even funnier than that. We realized that, okay, some people actually designed an ad hoc version of Dialectica for something completely unrelated, which is differential programming.
Okay.
And the reason is not completely unexpected after the fact, because if you look into what you can do with Dialectica, you can actually compute the derivatives of your functions. So somehow the ability to track the uses of variables in higher order functions is one way to implement differentiation at any type. So, I mean, probably it has been discovered several times by several people, because it's not completely crazy either. So
right.
You can reconstruct it from first principles, and once again, it's like the the Martin of type theory stance, right? Depending, we may discover the same objects several times. So actually, it's a very good criterion. If several people discover the same object several times coming from different backgrounds, then that probably means that the object is interesting.
Yes, right.
Or it is very natural.
Mm-hmm. So earlier today, when we were talking about the nice properties, and I think when we were talking about Gödel incompleteness theorem, you said something about CPS translation and how we had to talk about dialectica for this.
Okay, so the reason I wanted to mention that is related to the realizability interpretation. So basically, the reason Gödel got into the dialectic interpretation, like you can really, if you look into the, I would say, historiography of Gödel's work, you would maybe this is a bit of fantasy of my side, but I think Gödel felt somehow guilty of or at least there was something to be repaired after the incompleteness theorem. Right. And because basically it destroyed math. Exactly. Who is and the end of the story, what are you doing?
And he was pretty young too. He was 26 or something.
Yeah. So he tried to. So that's. Far from putting an end to the foundation crisis, I think that the Gödel's incompleteness theorem actually kindled somehow a quest for alternatives, right? And I think that Martin of type theory is a descendant of that quest, as through the realizability interpretation, because since you cannot trust your you cannot trust your systems, and because they are necessarily incomplete or indecidable, so you have to pick a meaning. So since you cannot trust your system, you have to find other alternative criteria for your for the validity of a proof, right? So a logicist would tell you, Hilbert was probably some kind of logicist, so he would say, mathematics are little games of you apply the rules, blah blah blah. The system is locally consistent, whatever. You cannot derive an inconsistency from the system. So good, it's just like you're playing Lego, right? But that's not since there is the incompleteness theorem. This kind of philosophical stance is a bit dangerous. Because then what's going to guarantee that your system makes sense whatsoever? Because in the end, you're always relying on a stronger meta theory. So you're just pushing the game of this little Lego game in the meta theory. So there's no good. And the finitistic approach, which is actually a thing culminated in the Curry-Howard isomorphism, is one way to solve this conundrum by saying that it doesn't matter. Actually, who cares? Okay, two considerations. The only real properties you care about are the sigma zero n properties. So the ones that say there exists a natural number that satisfies some decidable property. Because in practice, when you write a program, right? So you're a computer scientist, you write a program, you don't care about functions. Who does? A function is just an end to a mean to an end, rather than the way around, whatever. So you're using your function as a placeholder to compute things, but you never did printf a function you don't care about the code of a function. You don't care. Functions are just tools. The thing you care about is the concrete result of your function that you print on your screen or on paper in your printer, or you send through the internet on Twitter, who knows. But all we care about, both the programming language and the mathematical foundation, is that we only care about the concrete results from these things, the actual concrete numbers. And if you're a logicist and you have a completely crazy classical system, then you're very annoyed, because you have this Lego game that says there exists a natural number, go figure what it means, and there is no way to actually get anything out of that. But if you do a BHK interpretation, realizability, Martin of type theory, whatever, it doesn't matter. You just run your program, because there is already an implicit interpretation of the thing that computes. You run your program, maybe it will loop, because you actually got your meta theory wrong, because maybe your theory is inconsistent in the end. But if it terminates, then you will get something that satisfies the right property. So you don't have to trust Santa Claus existence floating in the void or something. There is a concrete way to actually extract what you were caring about. And
it's crazy to think how probably Gödel already understood all of this in the 30s, right?
Yes, he was a pretty clever guy. Yeah.
Right. Like, and now we're starting to really understand the depth of all of what he just didn't have enough time, and
Yeah. Well, that's
and didn't have enough tools either, right?
Yeah,
like the kind of logic that was.
There is I mean, okay, so Gödel was amazing, but I'm a bit disappointed by its contemporaries. It was like, and even further than that, like in the paper I was mentioning before, the scoring of logic by Bourbaki, actually you can tell that they do not understand Gödel incompleteness theorem.
Oh.
They make weird claims.
Right.
And this is like 20 years or so after the publication.
Right.
So even 20 years after the publication, they're completely oblivious of what it means, and they are still living in the pre-Hilbertian, like they live in the paradise of true mathematics, and they're completely.
To be entirely honest, it doesn't surprise me at all. Like I've one of the factors of why I do the podcast, that I started feeling like a lot of undergrads these days, they're leaving their university without ever hearing about the Curry-Howard isomorphism to begin with. So like they don't even know how what we're doing is deep, like it's rooted in mathematics.
Well, if you came from where I came in France, that's that was a stronghold of Curry-Howard.
Right.
Yeah, that depends on your background.
Yeah, exactly, because you're in France, but that's not necessarily what is going on there in the rest of the world, and that really surprises me. So not only they don't understand the Curry-Howard isomorphism, which is one of the most beautiful theorems in our field.
I don't think it's a theorem. It's
still. And so, let alone understanding the depth of Gödel incompleteness theorem. So, like, we're talking about our field, right?
So I don't think that. So to be fair, I don't think that. Okay, this is like starting to delve into a beer time discussions, but I don't think that Gödel's incompleteness theorem is very deep. I'm actually surprised. It took Gödel to prove it, so it was not obvious. But in retrospect, I would have been extremely surprised if it hadn't been the case. It was like, what's the point of proving the consistency of a theory inside that theory? It doesn't tell you anything about the consistency of that theory.
But Hilbert thought it would be true.
But okay, step back for a second. Imagine your meta theory is inconsistent. You prove from within the meta theory that is inconsistent, but your meta theory is inconsistent.
Right.
What did you gain? Like, okay, even if the Gödel theorem had been true, you wouldn't have gained anything from it.
That is a very good point. In any case, let's come back from the beer conversation, and I think I ran out of topics. This is starting to get on the long side, which is good, honestly. But is there what else should we touch here?
Did we forget anything? I don't know. Maybe some message for the poor PhD students trying to struggle their way through research. I don't know. Remember, life can be hard, and it's not because you're a permanent researcher. So I've got the privilege of being really an immovable. Like I cannot be fired or anything, so I could just vanish and stop doing research, and I think not much would happen. I know where. Okay, so that said, so this is all. So it's easier to say that from me, but I think that you shouldn't lose hope to some extent. Like I see PhD students struggling, and then postdoc it can be a very hard thing, and especially in type theory, because type theory is there is something quite sterile in type theory where, okay, this is more about academia, but there is since there is the pressure to publish, and there is some kind of lack of objectivity in type theory, because a lot of things so there are hard problems that nobody wants to tackle because they are really hard, and then there is the academia churning of papers, like you come up with a new system. Like Girard has a very good. So I recommend reading that paper as well. Like it's a very good parody of. It's in French, unfortunately. It's called. Actually, it has been translated to English. Sorry. Yeah, read Mustard Watches.
Mercy of the
mustard, like the mustard sauce. Watches, like
mustard watches.
Yeah, by not Jean-Yves Girard, a pseudonym which is actually Yann Joachim Ringard.
Okay.
He's making fun of something that hits pretty close to what we do in type theory, which is coming up with you take a system, you add some random stuff to the system, and then, look at that, I've got a nice system that does X. And And I think that a lot of students do not have the ability to rebel against whatever their advisors are telling them to do. Precisely studying this kind of mustard watches. I'm guilty myself of doing a little bit of mustard watches at times, but you have to be always careful about not getting too much into this mustard watches and not lose track of the greater thing you're doing. So yes, you need to publish papers and whatnot, but at least try to do something that you find interesting, you may find useful, and that contributes somehow to the accumulation of knowledge more than just churning papers somehow.
So would you say that do you have this like you don't need to publish papers to do
not
your
really
job, right? So would you think that it's fair to say that so you do it because you think you are contributing to knowledge?
Yeah. So personally, as from this very privileged point of view, I think that publishing too many papers is like just like you're drowning the interesting knowledge in a lot of irrelevant stuff, and it's very hard to review like all the publications that go even like PLT type theory. There's so many things going on that like less papers is bad for your career. But good for the greater knowledge and the actual good to society.
Oh man, you have no idea how much hope this gives me, because this is actually a recurring topic in this podcast, and how I've been since I decided to drop my PhD. And the reason why I'm keeping this on track is because like I grew pretty cynical about particularly the American education system, how the tenure track works, and how that all works, and how much pressure there is in the PhD students, like not only to publish, but the amount of workload they give on them. And that's because also it's coming from the above, because the professors have to have all of that.
It's basically a Ponzi scheme. I mean, the American, right. I mean, it's true. It's also true in France, but to a lesser extent. Like the American system is completely crazy, if you ask me.
Right. Yes. So coming here and hearing this, and like how I've got to be entirely honest. Like I've always, like, since my undergrad, like since the first time that I touched Rocq, I could see, like, for me it's the most complex, not complex, the most, I forgot the word, but like the greatest language that exists in the terms of expressibility, right? You can express the most amount of things.
It's not during complete,
Doesn't matter, right?
Okay.
Like it's the most sophisticated programming language. Most sophisticated programming language, with the most theory, with the most thing, the most stuff. It's incredible. It's beautiful. So I've always had a lot of esteem for you guys here. So like, and I'm very confident that there's a lot of people in the world right now in that same position, right? And you guys have no idea. Like, you guys here, and that's why at the beginning of the episode I call this the Olympus, right? Like you guys are kind of like protected from all of this pressure that a lot of the rest of the world is.
There is a negative side to it, which is really that as a student, when I was younger, I was very happy to learn a lot of things in a very short amount of time. Like in 1 year, you could learn like a good chunk of whatever Curry Howard, whatnot. Everything seemed brand new and like it was making a lot of sense. Then when you reach this Olympus, like the speed at which you learn new things is extremely slow, and precisely due to this publication pressure and whatnot. Then people have to churn out papers. But in reality, my daily knowledge is virtually, it's very uncommon for me to learn really new things. Like it's a very incremental things, like you read the papers and okay, well, we could have done it already like 10 years ago. Who cares?
Yes.
So,
but still, my point was that the reason why it gives me so much hope is because the feeling that I had at the end of this conversation now is that you're doing this out of love, out of like this, you see real, like, there's no pressure. You're doing it because you want, right? Like, because this is what you want to do. Yes. And this is what science should be for me.
Yes,
this is the idealized version of what science is.
I agree, but unfortunately, there is quite a gap between the idealized science and the actual science.
Yes. Of course, in the end of the day, that's the point. At the end of the day, science is also a humane effort, and as such is bound to be
Yes, but I think that it's so in the case that, okay, this is delving into political topics, but in the precise case we're talking about, I think it used to be like in France, you can clearly can see from the French point of view that there has been a collapse in the general science quality. Like France used to be a very specific island of like researchers having a lot of freedom, free time, like they could pursue any kind of stuff they could do. And this time is maybe not completely over, but clearly the tides have changed, and this is not something that doesn't fall from the sky, in the sense that there is the reason why it was nicer before and the reason why it's worse now is due to conscious political decisions.
Mm-hmm.
So yeah, it's
so like are you hinting in terms of putting money, like?
It's not even about money that much, because like research is like a minute amount of the gross product or something. Right. But more generally, like the rise of okay, there is a word for that. I'm sorry, but it's neoliberalism. The rise of neoliberalism as a way to actually put a metric on anything. Like to define the value of something, you need to put a metric on it. And once you put a metric, you take a crappy metric, precisely, and then you.
So this is what I was coming back when I was saying the argument that in the end of the day, science is also a humanitarian thing happening. Like it's also bound to the nature of our social relations, right? So whatever our current society puts value in, it's
current society, but it could be different, and it has been different. Which is like I'm not saying, I'm not like a fierce communist saying like tomorrow we will like partake in joy, whatever. It used to be better, and we did better. So.
But here's another argument, though. We had less access to higher education back then. So the group was much smaller, right?
That is true, although in the case...
I have this feeling that we're having a trouble in academia that we don't know what to do with so much people, so much information, so many PhDs, so many PhD students.
So in the case of France, I think France once again is so I see a sharp difference between the US and France there,
right.
And maybe other countries, but I know a bit less about it. But like the ratio of people doing PhD in France is abysmal. Like very few people do PhDs in like everybody. Like there is a huge amount of people doing master. I think it's like almost. It used to be a bit more than 20% of the I don't remember whether, and maybe I'm wrong on the numbers, but I don't remember if that was 20% of the persons reaching higher education or 20% of the whole cohort, which changes things. But if you compare, which is still a big number, if you compare that to PhD students, like that's below the 1%. So there is a 1 to 20 ratio. So and it's good, but doing a PhD shouldn't be an end in itself. Like you should be doing a PhD to do research because you like research.
But that's the thing. So like not only the PhD itself, but higher education starting from undergrad, it's unquestionable that like the access to doing university is much higher. So that since now in the job market, there are so many more people with undergrads, so now you need to get one more level of higher education, right? And now there's so many people with masters than more people. That's why in the West, there are so many people doing the PhD.
Yeah, in the US, it's pretty clear
that for example, in pharmaceuticals, it's almost impossible for you to get a good job without a PhD because of exactly this.
Inflation,
basically. Inflation of the knowledge. And I think this is a natural result of maybe the wealth being produced by humans. I don't know. But in any case, the problem that I see here is that we are drowning in the amount of people and the amount of information. And now I think we're even in a good spot in type theory or even programming language research in general, where it doesn't compare with machine learning.
Machine learning is crazy. Could be worse. Could be. I think that biology is like even worse.
So, but I feel all the sciences are somehow kind of driving there, right? This
probably,
and it's something that I've been thinking very hard, because I feel that like higher education now has this weird property where we don't know what to do with academia. We're not discussing this problem, right? Like, is it to prepare for the job market, or is it to do science? And right now they're collapsing in the same thing. That's why things are so weird. So that's a question that is open. In any case, that was a very good conversation. Is there any final things that we should wrap this up with?
I don't think so. I'm happy to thank you for the like the ability to rant for unreasonable amount of time about random things. So
no, I have to thank you. This was one of the best episodes I've recorded. Really.
Thank you.
I'm very, very happy. We should have done something like this much earlier on. I think we tackled from the foundation up and some very deep results and got extremely technical, but in a very good balance of explanation and what explained. And one note that I'm gonna make is that Pierre-Marie is even funnier off track. Exactly because of his rants, and he was extremely polite in this conversation. And make sure you pay him a beer if you meet him in a conference. Let's finish here. Thank you. That was it for the interview with Pierre-Marie, this 2-part episode. And I'd like to take the opportunity to really thank the Galinette team for receiving me in Nantes. It was an incredible experience. So the story behind all of this, I was actually in a summer school in Birmingham University, organized by Anupam Das and the Proof Society. And Pierre-Marie was over there, and we kind of hit it off. We had a bunch of conversation, and I was like... I pretty much just annoyed him that I told him I'm coming to visit you. I don't care. So I came over to Nantes, and actually it was very funny because Mario was actually visiting the same timeline as I would be in France. So things lined up extremely well. So as I was hanging out there, Mario was also hanging out over there, and we all had a really nice time. And I just wanted to take the opportunity to thank the Galinette team, to thank Tabarot, to thank Mathieu Suzeau, the Rocq developers at large. It was an incredible experience. I had an extremely good time. If you're listening to this far and you would like me to tell you more my stories in Europe, I just returned from this 40-day visit in Europe. I participated at ICFP. There was a summer school in Germany. There was the Proof Society summer school in Birmingham. There was something else that I blanked right now. So yeah, that's it. I'm considering if I will record an episode to share a little bit of my experiences in Europe and what I've learned about the differences between European style academia and American academia. They're pretty different, turns out. And like the research at large. But yeah, let's see how things go next year. I have some interesting plans. Come hang out with us in Discord. I share some stuff sometimes. We are having some really interesting conversations over there. The other day, someone was sharing some initial drafts about Automath and De Brown's ideas. Was it De Brown? I think it was De Brown. Anyways, yeah, if you're enjoying the show, don't forget to support us in our Ko-Fi platform. You'll find the link for that on typetheoryforall.com. You will... Any amount is highly appreciated. It helps us a lot. So go to typetheoryforall.com and become a patron for the show. See you guys next time.
Este podcast foi editado por Play Áudios.